recording started. Feel free.
Is it going? Is it working now? Okay, thank you guys. I'm here to talk to you today about something that bothers probably everyone working in this industry. Beginners don't know where to start when they see this myriad of programming languages that you can see here on the slide. Everyone asks, which language should I learn first? And everything. I have heard a lot of questions like that. And also experts, and I consider us to be experts. I hope we are. We also diverge, and probably way more than the beginners, about how to pick a programming language for a project, right? Of course, we all have our personal preferences, but this is a quite complex decision, and it doesn't. We never know what to do. We just pick whatever we like or whatever our company is using at the time, and then we are doomed, right? So my question here is trying to think a little bit about how this state of affairs came to be. And my question here in a more polite way is, how did we arrive at this mess that we are immersed right now? So my name is Edil Medeiros. I'm a professor at University of Brasilia, and my research areas, I'm actually a hardware designer by training, and I later started to study and like to work with this theory of programming languages and modeling of complex systems. So I'm kind of a hybrid guy trying to understand also what's happening in this area, in this industry. And I always like to start with the answer, or at least with what I believe is the answer. And maybe the guy that has the best phrase or the best quote for this problem is actually Mr. Winston Churchill. And he was arguing in 1941 or 1942 about the reconstruction or the rebuilding of the House of Commons, which was bombed by German armies at the time of the Second War. And he was arguing against reshaping the architecture of the building, in particular of the chamber that the deputies, that the congressmen there, they meet. And he was a strong believer that the rectangular shape in which there are two sides on the room, then you have to pick a side. That was one of the bases of the British democratic system. He strongly believed that you have to pick a side, and that the building, the environment we are in, it actually shapes how we think. And he was defending that position. And I believe this is a profound metaphor, actually. This was for sure not his intention when we was talking about rebuilding a place, to talk about the nature of human beings, but I believe he touched pretty much how we work, because we actually build not only physical tools to extend our body, but also intellectual tools to extend our minds. So if you think as mathematics, philosophy, physics, actually, they are all tools for the mind, and they actually made us something larger than just persons that we think we are, right? And in some sense, we become those mental tools. They extend our minds, but also they restrict our minds. They constrain our minds, and we cannot. After some time dealing with any kind of such a tool, we start to being unable to think outside the box, right? You have heard this expression before. That is to change your perspective on a problem. And our problem here, and it has been since the beginning, is what we call complexity. We are always, from the beginning of our industry, we are trying to build more complex systems, pushing more features, doing fancier animations, or doing whatever we call new into this industry. And our tool here, and I argue that this is the most important tool human beings have invented for extending our minds, is what we call abstraction, right? And we are always in this chase after our own tails. We face a new problem, a new complexity problem. We invent a new abstraction, and then we that allows us to push this complexity wall further, and then we invent new abstractions, and we are always in this endless cycle. And I believe this will be a no-end place. We are just have to live, and this is what we are. This is pretty much what we do on this industry. And I want to bring back here some history of how all of this came along, because I believe there are two guys here that are pretty important, and we talk very little about their ideas, and they shaped the way that the whole thing is taking place right now. The first one is this Mr. here, Mr. Alonzo Church. In 1932, he was trying to solve a fundamental problem in mathematics, which is called the Unchidon's problem. And it's not hard to understand what actually it is asking in this problem, which is something in the lines of, given an arbitrary statement of what they call the first order logic, it's restricted kind of logic. The problem asks you to decide in a finite number of steps if there is a proof of this statement in the logical system, right? And this was an open question until 1932, and Alonzo Church invented a system we today called lambda calculus. Actually, he already called that name at the time. And his conclusion on this mathematical problem was that this is actually an impossible problem. It doesn't have a solution in general. And that was like a breakthrough result in mathematics. But we are much more interested in the tool that he invented to solve the problem, because that's the basis for thinking about problems. And this is the basis of what we today call the functional programming paradigm. And you see, I don't need to go too deep into the importance of functional programming. Everybody's talking about this, and we are going to talk way more about this in the future. Lambda calculus is actually a very, very simple system, which is a formal system that has only these three syntactic constructs. You have the notion of variables, which only make sense on the context of this other construct, which is called abstractions or lambda abstractions. These are by no means similar to what we call variables in programming, which are places in memory where we store some kind of data. There is nothing like that here in the system. And the last one is what we call application. And there are only two rules in this system, what Church calls the alpha conversion and beta reduction. And I kind of like those names because they sound fancy. But for normal people, we might rename them for variable renaming. So in the system, we may rename variables, and that's no problem. Actually, this is a technical necessity to avoid some technical problems on the system. And the second rule, which is the most important one, is variable substitution, which just says that if you have a lambda abstraction and an application on the left side of the beta side arrow, you drop the lambda x in the term. So in some sense, it simplifies the whole expression. And then you go into this m expression and replaces all occurrences of the variable x, this syntactically x for whatever e that you gave for this, what I will call a function, right? And the inspiration here is pretty much what's happening and what we learned on mathematics on basic school, actually. When we say something like f of x is equal to x squared, we can do pretty much anything with this other than give it a value, for example, f of 2, and then substitute x for 2 in the expression of the function, and then perform the calculation. So this is pretty much the same thing, right? And even though it's extremely simple, just like in mathematics of functions, and you all probably studied calculus and real analysis and complex analysis and all that things, that simple concept can go very, very deep and with very profound consequences. And this is pretty much the same of what happens here in the lambda calculus. So to illustrate for people that probably don't remember or have never seen this before, let's take, for example, those three lambda expressions that I called true, false. Those are arbitrary numbers, but of course they try to carry some meaning for me, at least, that wrote those formulas. And I have another term here that I called the end, and I claim that those lambda terms here, they model true and false statements in logic, in Boolean logic, for example, and the end is the model for the end Boolean logic. And how does it work? If we want to evaluate, for example, and true and false, for example, and it's just a mnemonic, so just go and substitute this expression. And the first step here is to apply beta reduction and substitute the p variable in the first expression for true, which is the first argument that we are passing there. And the same for the q variable, using another beta reduction. Then true is just a mnemonic for the lambda expression. So doing another beta reduction, we reduce for this, and doing beta reduction again, we arrive at this final expression that we have nothing more to do with it. There is a function, right? But we have no argument, so that's the end. That we have nothing more to do with this thing. So we have to conclude that that computation there, that program that we wrote in the first line, computes to this result, which is false, which is what happens in the Boolean logic when we try to calculate true and false, right? And if you try all the other cases here, you will see that all agree with intuition from the Boolean algebra. And this is how we start to embedding other stuff, other knowledge into this lambda calculus framework of thinking and understanding computation, right? And what happened here, even though it's very simple, it has some consequences about what we were doing here. First thing I think it's extremely overlooked is that we use the same language to describe the computation and the and, true, false there, and all the lambda terms and applications. And we use the same language to reason about the computation. We go computing the thing, and we never go out of the language. We never rely into some kind of machine or memory or something that is not described already in the language. Everything is there, crystal clear for you to see every time. The second thing I believe it's important here is that semantics is extremely simple. It's based on this substitution rule, and it's pretty much the only thing that you can do. You have a function, you give it arguments, and you substitute those arguments into those variables in it's syntactically done. So we deal a lot with input-output relationships. So we give functions inputs, and then we calculate what comes out. And that's the only thing that we can do. We cannot, those functions, they have no knowledge of anything that is not their arguments, nor they can do whatever, anything other than generating its output. So there is no writing on the screen, there is no launching the missiles, there is no whatever you want to do on the external world. This is what we call the pure computations. Data is inherently mutable in the system because if you solve it, we never destroy the information. Every time we apply this beta reduction rule, we create new information. We add a new line into the computation that we are doing, but we do not destroy whatever we have done before. This is the immutable sense that I'm using here. And finally, and I believe this is a huge problem, at least in a practical sense, and I believe this stopped this system to be used in practice for a long time, is a problem that evaluation order is ambiguous. You can take what to do next is a decision for someone that is out of the language. In my case, I was evaluating the thing, and I chose the order that I was doing the substitutions, but I could have chose another orders on that example. If you go there and try to find them, this is not a theoretical problem because we have theorems stating the unicity of the final computation. So if we can arrive in the final computation, there will only be one final result that we will get. But this is a practical problem in practice because we want machines to perform this, and machines don't take decisions. Humans take decisions. Machines just do whatever they are programmed to do, right? And for anyone that wants to know a little bit more about this topic here, I strongly recommend these two books. The first one on the left is a classical book, not about the lambda calculus itself, but about formal systems and how powerful they can be to describe extremely complex phenomena, including our cognition. And on the right side, you see this is also a classical textbook about specifically about lambda calculus. And so this is my recommendation. And that was it on 1932. That was the state of affairs. Lambda calculus was our notion of what we today call a computation. That was the model of computation. Whatever the lambda calculus described was called a computation. Until we met this guy, Alan Turing, in 1936, which is the year where he publishes a paper which was trying to solve the same problem, the same Unchidon's problem. And unfortunately, or fortunately for Mr. Church, he already solved this problem. But fortunately, the guys on the scientific community decided to publish Turing's work, even though they arrived in the same result, just because of his novel methodology of solving this problem. And we have to thank these guys because otherwise we would have had to wait maybe some decades more to have what we call computers today. So what Alan Turing did, he imagined a mechanism instead of a formal mathematical system that lives in our minds, a set of rules. He imagined an actual mechanism. And of course, this is an abstract mechanism, but it's you will see it's pretty similar to what a machine would do. And actually, he called this logical machines, right? And they are heavily inspired on typewriters. They have what we call a finite state machine today, which is pretty much trying to capture the intuition or the actions that a person is performing when they are trying to calculate something using pen and paper. And of course, if you have a person using pen and paper, you need the paper. So the finite state machine has access to in this case, an infinite tape, which acts as an external memory for the finite machine. And This is not how we describe this nowadays, but Turing used this kind of tables that I designed one here for the same AND function that I showed you before. And from this kind of tables that you can find on his paper, we infer that we have to perform, this machine has to be able to perform at least or exactly these 4 operations here. It has to remember its actual state. And today we would call this program counter, something, a register or something that keeps track of what am I doing now, right now, right? And the analogy I like for this actual state for non-programmers is sometimes we are reading a book, a physical book, and we are using our fingers to track where we are. And our finger here is acting as the actual state of the program counter for this reading computation that we are performing. Next, we have to be able to scan a symbol on the tape. We need to read from memory. This is what we would call today. We should be able to perform some kind of action. And if you go see in the paper, the only actions that the machine actually performs on Turing description are jumps, right? What we call jumps today in programming languages, in programming parlance, and writing into this memory, adding new information into this paper, this piece of infinite paper of this tape, of this memory that this machine has access to. And finally, it has to update this state, and it has some means to decide, okay, what should I do next? I just performed something. What should I do next? What's my next step? And if you go into the computation, it's extremely simple as well. On this example, it's the same AND function that I showed you on the lambda calculus, just to see how different it feels to compute on a Turing machine. We start with the machine in this A state. We read a symbol from the tape. It's the actual symbol right now. It's the symbol 0. The table tells us that we should move to the right into the tape and go to state B. And then we perform that action. In state B, we read what's on the tape right now. We are seeing the symbol 1. The table says, okay, whatever you see a blank space there. Whatever you see, go 1 space to the right and move to and update to state C. And then we do. And on state C, the table says, okay, write a 0 on the table and move to state F. Update to state F. And state F is a halting state in which the machine just say, oh, I'm finished. You can imagine that there's an alarm or a LED or a sound, a buzzer or whatever that says, okay, the computation is done, right? And that's the result of the thing. This is the notion of computation on this Turing machine model that we use. And there is some catches here, because if you go into Turing's paper, it's kind of hard to read and you don't understand things at the beginning, because he was actually interested in machines that never stop, they never halt, right? But that was his approach to solve that mathematical problems. When it comes to software, we want our machines to finish the tasks that we ask them to perform. So we are actually more interested in machines that actually halt, that stop, that when the computation has an end. But this is not only the only contribution, and probably the most profound contribution from Alan Turing is actually something that is also on his paper, which he calls the universal machine. He invented a language, a very convoluted programming language, if you will. And he uses it to describe the structure of an arbitrary Turing machine. He invented this, pretty much inventing a language to describe those tables, and then you can transform them into strings of symbols. And then he also invented or designed, if you will, one specific Turing machine that is able to read this description, this table description, which is something that describes another machine, and perform a simulation of that other machine. And it's kind of confusing because it's kind of meta, which is a machine that can emulate other machines. So it's kind of confusing. It's a brilliant software, if you will. I would call that a software engineering problem. And it's very interesting to go through the paper and see how he solves this problem, because he invents a library of useful functions just like we do today to solve and builds a framework to solve this specific problem. It's very interesting to see that happening already in the 30s. Years before, we had the first actual physical machines we call computers working and operating. And if we go and read what was happening here, we can say that the semantics, what means to compute, is heavily based on this abstract mechanism. It's something that I would say that you cannot understand any program in this paradigm if you cannot understand, or if you cannot simulate in your head what the computer is doing, what this machine is performing, or at least would perform after you gave it this program. So you need something external to the description of the program, of the description of computation. And this is actually quite confusing. This is the initial barrier beginners have when they start to learning to program, because they have to enter this mode or learn to enter this mode of thinking as the machine, like simulating the machine in their heads. Right? And this is also how we reason when we are programming, especially when we are debugging software. We are debugging and going step by step, line by line in our program, and say, okay, what's happening here? What's the state of the computer after this line, and after this line, and after this line? This is exactly what we are trying to do, simulating in our minds the functioning of a computer. Also, this is heavily based on memory manipulation. So you also cannot understand what's happening without keeping track of what's happening in this external thing. And this is an external thing for the external programming language, which is the memory, which is an external thing for the machine, which is kind of, you can see how abstract this can go when we are trying to think about these things. Data is immutable by definition here, because we can overwrite and we can re-erase what's written already on the table, on the tape. So if we don't move the head there and overwrite something that's already written in the tape, we lose some information that was already there, right? So of course we can apply some discipline on ourselves when designing these machines to not go and overwrite something that's on the tape already. But you can say there is nothing in the system, there is nothing in the model that constrain us from doing that. This is a discipline. This is a self-discipline that we have to agree upon us if we want to. But this is pretty much a problem also, because many efficient implementations for many algorithms, they are only efficient because we can do this in-place mutation. So this is a kind of something that makes things harder to think about, but also this is a tool, this is a practical tool that we use all the time. And finally, evaluation order here is unique and unambiguous. There is only one thing to do at any time, and it is based on the table that describes the system. And I believe this, you see, all this description made way easier to use this thinking model, this model of computation, to actually build machines. And if everyone, I really recommend this book. This is a quite obscure book from Charles Petal, in which he goes phrase by phrase on Turing's paper and read it with you or for you, and that explains, okay, what he's trying to say on this phrase here, what's the background for the problem that he's stating on this paragraph there. It's a very interesting reading. It's supposed to be understandable by non-programmers, so it's just go there and take this book. It's a very, very, very good reading. And that was the state of affairs in 1936. We had these two kind of competing models of computation, but they were only trying to solve problems in mathematics. Turing itself, in the same year, 1936, he proved that both models, they have the same computational power, if I can use this expression. They can describe and they can solve the exactly same set of problems. So they are, in a sense, they are equivalent. So which one you pick to solve a problem is pretty much whatever. Choosing a programming language today, it's you do whatever you are more comfortable with. Until in 1945, about a decade later, John von Neumann started working on the EDVAC project, which was an electronic computer at the time, one of the first ones that was actually built using vacuum tubes and all those kind of old stuff electronics. And this guy invented and he designed what we call today a CPU, a central processing unit, and all the circuits that go with that with it. He went way more than just saying how things are supposed to be organized, but he actually designed those circuits. And the computer was actually made and manufactured later. And this is pretty much what we are still doing today. He invented the idea of instructions. He invented the idea of a single memory for data and for programs, and how does it interact with the CPU, and how do you input data into the system, and how do you output data from the system. He invented pretty much everything. And I would argue that work was the first, what I would call a pseudo programming language, which we all call assembly language. And assembly language is not exactly a programming language. It's actually a description. It's more a description of a system architecture than an actual programming language. But this is something that you actually write, and you can code software for a specific machine. So that was the first step of engineers taking some ideas from the mathematical world and actually implementing something physical, something real. And this was actually the first time we had programmers doing programming just like we understand today. Programming for the sake of programming, and not only for the sake of trying to solve a mathematical problem, just like Ada Lovelace and others did at their time, and they are called programmers as well. And then we start a whole series of new programming languages, and each time we are trying to solve problems and by means of inventing new abstractions, right? So the first important next step here is the Fortran language, which invented structured programming, which we called here, it's the first important high-level programming language. Instead of dealing with the machine instructions themselves, you go and use things that we use still today: if statements, for loops, while loops, go to, jumps, something that we don't use today, but they are there. The equal sign as an assignment, as a memory reading and writing operation. And Fortran is still in use, of course, in a modernized version, but it is still in use. And Algol was the next step. And Algol was an academic language. It was not intended to be implemented and to be run into computers, but only to make all the algorithm descriptions on academic papers uniform. They should all use this same language to unify the works on academia. but he invented a lot of things too. For example, pretty much all modern syntax that we know today was invented here. What we call C-like style was pretty much algo already. Scoped blocks of code. So we introduced this notion of scope into the syntax of our code, and the notion of types. And of course, types here, they are very simple types, ints, floats, and characters, but it already introduces this notion of types and type systems to help a programmer to program, to do this thing. Next in the line is Simula, which is today a quite unknown language, but it was the first time in which we heard the expression object-oriented programming. It was in 1962. And in 1965, this paper came along because, and I wanted to point it to you guys, I'm showing you just the most important languages of their time, but at this time already, there was a huge number of programming languages, and programming languages for all tasks that you can imagine, that we call today domain-specific languages, languages for all tasks that you can imagine. And Peter Landin here, he said, he was arguing that we should, instead of designing new languages, design a very good functional, I can't remember if he calls it functional already here, but he said he would be, the language should be inspired on the lambda calculus, and it should be the vessel for designing the other domain-specific languages. Unfortunately, nobody heard him, and we kept designing more and more languages. Smalltalk was a very important language that introduced the idea of process virtual machines, and it was like the first time that someone talked about something similar to a JVM, right, that we know today. So this is an important step there. C is one of the most influential languages from all times, and it doesn't introduce too much novelty here, but it was the language used to build the Unix system. So it was the de facto standard for building for systems programming. So it kept this history. Then we start to see C++, trying to incorporate ideas from C and extending, and Objective-C, which is Apple implementation of these ideas. Next, we had some other important languages floating around that gained a lot of importance with time. Java, with the idea of actually implementing a good JVM, a practical virtual machine, a performant one. C# was the Java for the Microsoft ecosystem. Microsoft doesn't like me to say to state like that, but it's the truth. Python was already there in 1991. It was intended to be a scripting language, and it slowly gained traction, and then we see Python as a huge language, but it's pretty much what we would expect from a scripting language, which is acting as glue for other components written on other languages. And finally, JavaScript, which became the language for the internet in 1995. And on the lambda calculus side, the progress was slower, but I believe the ideas that came from there were really, really influential and kind of revolutionary that we are still trying to understand today, right? We don't understand what's happening on that lineage on the left side there. Lisp invented what we call automatic memory management, or garbage collection, if you will. Dynamic typing, which Python uses, JavaScript uses. The idea of having a REPL, something that an interpreter that you write and program iteratively. You play with the interpreter instead of writing a program, compiling, and then trying to see what happened. And he also invented macros and something that we call today meta programming. That the language has mechanisms to extend the language itself. So you can invent new syntax without messing with something external to the language. And this is something extremely powerful, but also something that we are trying to understand. It's not that everyone that knows or that feels comfortable doing meta programming, right, Lemos? And Mel, in the 70s, introduced what we would call today a strong type system based on this Hindley-Milner type system, which is a specific type kind of one, which is also implemented in Haskell. He introduced the idea of pattern matching, currying, and it was the first language which was fully formally specified. So it had an abstract specification that we can actually check if the compiler is doing the right thing. And finally, Haskell, it was introduced in the 90s by a committee, and all languages that were introduced by committees are pretty much dead today, but Haskell, which is a strange thing, a weird thing in this industry, and it introduces the idea of lazy evaluation, or call by need, if you prefer, which we are still trying to understand, which is something that it's hard to use in practice, and the idea of type classes, which is a disciplined way of doing polymorphism, way more disciplined than POO. And then what we are now in what I call the age of hybrid language, and hybrid in the sense that we are trying to build languages that blend ideas from both lineages that I show here. F# is kind of an implementation of ML in the Microsoft .NET framework. Clojure is Lisp running over on the JVM, and Rust is a systems programming language. It does pretty much what C does, but it introduces and it brings with itself the idea of a strong type system and type classes they call traits. It's not exactly the same, but it's the same idea. It's the same purpose. And this is pretty much the state of affairs today, right? This is the map of what happened and where we are now. And I would say that those guys would be quite impressed and confused with what we achieved. But in the end, it's not a very hard thing to understand. We were trying to solve problems, and problems arise, and we invented new tools, a new tool to solve a problem. And then comes what I would call a problem. And people misunderstand this. We never invent tools from scratch. Sometimes we invent new tools from scratch, but the normal way of doing inventions for human beings is we take something that a tool that we already have, and then we incrementally make it better or add a feature to it. And then we start to have all this legacy coming and hanging in our languages. And of course, from time to time, someone rewrites the thing from scratch. But even though if you take a very modern language like Rust, for example, you will see that you can perform just like you can write software that looks just like C in Rust, and it's perfect, valid, and Rust here. And what we are trying to do today, because people would say that code, that Rust code that I just showed you, would not be what they call idiomatic Rust, or it's not the right way to write Rust, right? And if I show you a program in Haskell, which is in the screen right now, which solves the same problem that the other program, the approach is very different, because here we are not thinking about iterating over elements of an array with that while loop there. What we are doing here is we have a list with numbers from 1 to 10, and we are processing this list as a whole. Just like John Bacchus argues, we are first filtering the list or eliminating some elements. We are mapping, we are doing something with the elements of the list. We are modifying them, and then we are summarizing all the elements, summarizing the list into something. And here we never talk about the elements of the list. And here we talk about the elements of the list, which is this I element here that's on the screen right now. So this is the what we would call the functional way of solving this same problem. And we can do this exactly same thing in Rust. This is also valid Rust code that works pretty much the same way. You have a list and you perform operations on the list, and you pretty much never talk about the elements of the list by themselves. And this is what we are trying to do nowadays. Raise the abstraction level. Instead of talking about pieces of data, we are trying to perform actions on whole pieces of data. And this is pretty much what we call today a functional approach or a functional style to solving problems. And this is actually a very powerful approach. This is a snippet from one project, a side project that I maintain that's called Rust in Pixels. And the same code here, changing what this style type means, and changing that and executing the same program, I can make this kind of image, which is a recreation of a classical piece by a generative artist called Manfred Moore from the 60s. He was actually trying to program this kind of things on computers generatively, but also generating this other kind of image, which is absolutely different. It has an absolutely different structure, which is a representation of a chaotic attractor. So it's a completely alien idea from the first one. And this is the power of abstraction. The same thing can start to mean different things. And by the way we describe how data is actually not how, but what data means in our system. And for the sake of time, Limbs, I will skip some things here and just recommend for everyone that is interested in learning more about Haskell. The first book on the left is I believe it's the best introduction to Haskell, because he talks about this idea of algebra, of programming, and programming, just like solving equations in algebraic systems. This is a very interesting idea that I'm still eager to see implemented or in our day-to-day work. And the book on the right is a more industrial approach to Haskell and to, okay, let me show you how to do those mundane things like accessing databases and APIs on the internet and stuff like that, instead of just dealing with mathematics and this mental stuff. So this is it. So I'm open to chat, and thank you for the time.
Pretty good. Congrats.
Yeah.
So I do have a question, but I will allow the other ones to go first.
I also
So
have, but I don't know
questions.
if I have time.
I'm gonna go ahead because I also have a question. So, you come from a hardware background, so
Yeah.
there seems to be an awful fixation on languages and not as much on hardware because we still use the same von Neumann machines as
Oh
we did in
yes.
the 80s, but they're just like super fast and stuff like that. We used
Mm-hmm.
to have like Lisp machines, which were a slightly different architecture. Uh,
Mm-hmm.
why am I wrong to say that there's not as much effort in exploring other computational paradigms in the hardware part?
I would say you are wrong, but you are wrong in a wrong way. Let me
Right.
explain. Uh, what I see nowadays is instead of people trying to implement hardware specific for this, I would say weird languages like a Lisp machine that you cited, or there was a Java processor sometime in the past as well. People are trying to do other forms of computation and trying to integrate this with the von Neumann architecture. For example, today you can have analog computers or analog hardware performing some kind of computation, and the results are read by a traditional computer, and they work in tandem, if you will. And there are other and esoteric kinds of computers, if I would say. For example, I have seen it's not long a time ago some people trying to use bacteria as computational units and actually integrating them with computers. So there are some electrodes that go, and there is some bacteria, and they do some stuff I cannot understand, but they are performing some kind of simulation of complex systems using the bacteria. And if you also understand that we are trying to implant things in our brain, so this is also a kind of hybrid computer that uses our brain to extend the computer, or the computer to extend our brain, or both, right? So I believe that something else, something new architectures and new ideas of what a hardware would be, will come from those approaches, which are more esoteric on one sense. They are more risky on the other sense, right? But I believe there is a huge problem with all of them, which is how to describe computation on those weird systems. This is the how do you understand those systems in terms of computation? So this is a huge problem, and nobody has a good answer, at least for now.
That's interesting because I was thinking of GPUs, for instance, and it feels like a lot of those heterogeneous hardware, a lot of them just act as black boxes.
Sure.
So you call like an API or something and get a result back, but you don't program on it specifically. So this is kind of sad, as like doesn't feel like we're pushing that to the limit.
Yeah, it's pretty much it. There is something that is implemented in Apple system they call MPUs, which is
Oh yeah,
neural
neural
something, right?
engine.
Yeah, I have no idea what are those things, but they are digital hardware specialized on matrix multiplications and stuff that they do on for neural networks calculations. So it's also works pretty much as a black box. You give it data, you give it the matrix that you want to multiply, you give it the neural network description. It performs the inferences and all the machine learning thing, and then it returns on the programmer's perspective. It's like an API. You call something, hardware do something, and returns a data for you, and it works like magic. So you see, in the programming language perspective, we are not adding anything new,
Yeah.
because this new hardware is like APIs. If you have a function that performs the same thing, it's indistinguishable. It doesn't extend our minds about thinking about the programming problem. This is, which is sad, but if you think about it, it's a very reasonable way to do it, right?
Pragmatic,
It's easier.
right?
It's easy to use it. Yeah, because it's easy to use. It's kind of plug and play.
Can I ask?
Yeah.
Right. So I have a question, but I think I need to develop a bit. So when you're presenting, I was thinking it's very remarkable to me that in the databases realm, the history is very much the same. We have like this supposedly SQL, NoSQL mess.
Yeah.
And very few people they even bother to bring up the relational model, which here I think we can make analogous in the same story, right, to the lambda calculus. if you think it that way.
Mm-hmm.
Uh, and at the same time, like we have practitioners picking sides on terms of what those things, of what those technologies they promise to give you back. So like okay, I'll pick like an NoSQL thing because it's going to give me this or something like this. So at a certain point to me, it starts to sound like more of like ideology. But here's what I think I'm very much more concerned with this is
Mm-hmm.
that most of the time understanding the theory that backs it up is not the priority. So you end up with something like you pick, okay, let's do relational, but then your relational means, okay, let's just use SQL because SQL is analogous to having a table or something, which is not true. And then like people start developing like these wrong abstractions on top of stuff. So, um, and here's what I would say, like that is the same thing that is reflected to me into Turing's approach, because what Turing was doing there, and I'm not blaming him by the way in particular, but I think the abstraction there is on the same level of being a practitioner. Like you are not
Mm-hmm.
thinking abstractively about the terms, you're thinking of how to apply that, which it,
Mm-hmm.
which can also be valid, but that there's a distinction there. So, uh, but something is very unclear to me. There seems to be a common cause for all these issues that we see. Like I see this issue on a grammar professor that that I like, Richard Mitchell. He mentions this same problem in language, for example. Um, CG date in databases. He mentions this a lot as well. So not to push it too much forward. So here's my question. I think I have my causes, and I would say it's our educational system. It's focused to be pragmatic, focused to be action. Um, so it's not really much concerned with like these other topics. Uh, so you mentioned that you mentioned how we shape our how our houses shaped the way they are. They influenced us. But for
Mm-hmm.
you, what did shape the houses? That's the thing that I think is still unclear.
Man, in this case here, that is a that is a question.
Because you see the problem, right? It's like that's
I
a recurrent problem I see in many ways.
I
So there
kind
must
of
be a common.
Yeah.
I kind of have a feeling it's trial and error though. The first shape of the house,
Mm.
you tried it and like you throw it and it glued to the wall. Oh, this glued. So let's develop on top of whatever we throw at the wall and it glued. So I kind of have a feeling it's kind of try and error the first shape. Maybe I'm wrong, but that's just an intuition.
Okay, I'll
Yeah.
let you speak.
Let me think about it a bit, and I will think about it loudly, and might be
I don't
just
think it's trial and error, by the way.
eh, yeah, yeah. I understand that there is some trial and error, for sure,
Mm-hmm.
but there are also there are a lot of educated guesses, even on the beginning of the shaping of these tools. For example, for use this specific example that I used here on Turing and Allows and Church Works, they were trying to solve a specific problem with a specific setting on logic. And if you go and study a little bit of the logic and how it was described at the time, using formal systems as well, I believe they made these educated guesses that okay, if I'm looking for a result about a formal system, I need a formal system to look for it to build this result. So if you see, it's kind of trial and error, but it's an educated guess for the thing. There are also a third model of computation, which is actually which came before Alonso Turing work, which is called a theory of recursive functions or
From
something.
Goldorn.
Yeah, or something like that. this theory of continuous recursive functions. I have never understood this thing. This is hardcore stuff. It is not as formal system like Church tried to approach the problem, which is he actually used real analysis tools, which is another field in mathematics, to solve the same problem. And he actually solved this before Church, but nobody could understand his proof. So you can understand that became like something that it stayed an unresolved problem for quite a long time. And this is the first thing. I believe there is a lot of trial and error, and on this trial and error, a lot of educated guesses, because the people that are trying to solve the problems in the community, they are practitioners, right? They know the problems. They know the problems very deeply. Nobody invents a database system if he doesn't understand deeply what problem he's trying to solve. Of course, you can design a bullshit thing, a shit system, but at least you have to understand the problem before coming with even with a shitty solution. So I believe this is the first thing, and there is a tension here as well, especially in this area of computer science, which is, on one side we have industry, and industry is not trying to invent new knowledge. It's trying to solve people's problems. You're right, in specifics. Sometimes you have to invent new knowledge to solve a specific problem. Sometimes. And we have the work in academia, which is trying to figure out new knowledge, trying to find universal knowledge, trying to understand things universally. But, and I include myself in this, we are professors, we are teachers, we are lecturers, we are researchers. We are not solving people's problems. So we have this tension, because people that have the time and resources to think, this is our function, to think about things. We are not the specialists in the problems we are trying to solve. The practitioners are. So you see a lot of this is also this. I don't have a conclusion for this thought that I just stated here, but I see these two tensions working: trial and error with educated guesses, and practitioners trying to solve specific problems versus academics trying to understand what's happening, but they are not.
That seems to be pretty unequal, right? Because who sets the standard? Well,
sure.
It's the market
Yeah,
who
sure.
set the standard, right? So
Of course, and we are all the market.
I want to know Mageta's answer though to his own question.
no, well,
Yeah, well,
I don't know if I
curious.
have.
No, you
I would
said
say-
it's not try and error
No,
because
I don't think it is solely trial and error. That's
no,
what I'm
but
saying.
but you also
describe
said
it
it's
to
not
me.
only try and error.
No, okay. Describe it to me again. What do you mean by trial and error?
I'm gonna try to use answers. So we have some sort of educated guesses on what we think is gonna work. Basically, heavily based on experience and our past contribution. So what we already developed before, all the formal systems that we already have, and then potentially all these past contributions, they will give you an educated guess that you can, okay, based on this I will try to make this. I don't know if this is going to work, and then you try that out, and then if that works, you're going to try to develop on top of that. You're not going to throw it away.
People usually despise this trial and error approach, but I constantly argue that this is the only way we have to learn, and what I'm saying is extremely controversial, right? Because of course we can reason and use reason to envision
Yeah,
solutions
I get
for
what I mean.
stuff.
Like,
But in the end, the end proof that something works or not
is
is
doing.
going there, implementing, and
Yeah.
see the thing in the physical world, right?
I totally agree, and that's why I think that when I criticize like this idea of being pragmatic and everything, I think people often think I'm just bashing, like
Ah,
straight away bashing, like, oh, okay, you shouldn't be pragmatic, you should just
ah,
be thinking all day, which is not true. I think it is a
yeah.
complement of reasoning and trying. It's not really just
See
discarding
what
one,
you're saying.
you know. So
I have a
No, I see
I
what you're
can I have
saying,
a
and
follow up.
I agree. I totally agree. I totally agree with this. You have to think, but also you have to do things,
yeah,
and doing drives thinking, and thinking should drive doing, right?
yes, exactly,
Just to
exactly.
just to communicate that to Edu, every single time Mageta says the word paramedic is like a
Oh no,
meme.
no.
So I have a follow up to Mageta's question though. Because what he said, I also totally agree that people they are pushing and pushing for practice and pushing for practice, and they stop thinking about it. And then
Uh-huh.
this is very common that you have, I don't know, people in the industry, and you ask, why are you using this? And then the person just says, oh, because everybody uses, or because I know how to use it, but they don't know how to
There
justify
are
it
some
with
other reasons,
reason.
like it's easier to find people to hire. If
Yeah,
it's like
also
that's another
that.
reason.
That's another paramedic reason
Guys,
for it.
this is our human nature. You know, there is a study, a very interesting one, which took some monkeys and put a rope and something, some food. They had to climb the rope to take this to access this food, and each time one monkey was almost there at the top, someone went and shoot something and the monkey fall into the ground, and they did this for some time. So, and after some time the monkeys learned that it doesn't matter if I try to get this thing there, something will come and shoot me to the ground. And then the guys on the experiment introduced new monkeys which never learned that thing. And what happened was, whenever one of those new monkeys tried to climb the thing, the old monkeys would take them and grab them to the ground and push them to the ground. And it's something that we of course this is on monkeys, but we are not that different from other animals, especially on the sense that we learn things and we stop thinking about it after some time, and then we just react, we just act, we just behave, right?
Exactly. But that's the
Yeah,
issue. That's
This is
exactly the
but
issue.
this
yeah,
is nature, this is our nature,
yeah.
we are like this.
That is a good point because if you like going back to dialectics in the Greeks, like they define the movement of the mind, like knowledge, gathering knowledge, as a binding between sensibility, right, the outside, getting stuff from the outside, and reasoning about it. I have a feeling we're just speaking we're just throwing away the reasoning part and just
Yeah.
keeping the praction the the practioneer portion of it, which is
Yeah.
Dictionary.
not which by the way also has reason. You for example, like, oh, okay, like I will it will be harder to hire people. That's also a reason, but it's not the transcendental reason. You know what I mean? Like you're not thinking
Yeah.
of the abstractive part of the thing. You're just thinking of the practical part of what gives you reason to
Yeah.
do such. So
Yeah.
Yeah,
Then
but
the
this
question.
glues perfectly with my question because what I want to ask is,
Yeah.
given the presentation and given Maguetas and Breno's question, which actually helped me to make my own, I think that the only way, not the only way, but it seems to be the best way that we. I have a feeling, and that's what I want to confirm with you, is that in order to grow and to discover something potentially better and something that we can potentially reason and justify, we need to be willing to throw it away what we already have.
Oh yes.
We need to potentially say,
Oh
be honest with
yes.
ourselves and say, what we made worked, but this is not good. We need to be
Or
humble
at least
enough,
it's not, or at least it's not good for the future.
or in the long term, because in the part of the on the diagram, for me this is perfectly drawn because we have a lot of orange arrows, a lot of things based on Turing's work, and then on the other side we have the people that say, okay, that is not good enough, and then we have Lisp and Mel and Haskell on the left. And I think, man, if those people they were not willing to um, combat, like go against the Turing model, we would never have tools that today's are like the must-have tools: functional programming, strong typing, macros, and stuff like that. Because they didn't accept the status quo back then, and they developed something based on the other party. That's why we got those features. And I have a feeling that
Yeah,
at some we're gonna have to do this again and again and again.
I call this a revolutionary mindset, and it has a lot of implications. But we need some kind of, I I'm not a I'm extremely suspicious of revolutions on any sense that you can imagine. But of course, I understand that sometimes it's good to have people arguing or trying new things and saying, okay, what you're doing is bullshit, and I am going to try something revolutionary. Revolution in the sense, this is absolutely, this is totally new. I'm not taking anything from the past, or if I will, and I will make something new from scratch, right? And for this, we need new people into the system all the time. But if you have to, we also have to understand that there is a cost of doing this, because when we are trying to figure out new tools, we are not solving problems, right? When we are trying to make a new hammer, we are not hammering nails. We are not making houses. We are not making boats. We are not building stuff. And at the end of the day, what drives us, our style, our lifestyle is building stuff, right? So this is something I don't claim I have a definitive answer for this. This is more on the politics side of discussion, right?
Well,
But one thing is clear. This is one industry, programming languages and computers, and especially programming languages, which which is what Hayek would call an spontaneous order. Everyone can come and do and try things, and if other people likes it or understand that that is the way, they can go into that direction. But nobody, there is no regulatory entity of any kind on the programming language world saying this is how a programming language should be, for example. This is a completely chaotic thing and spontaneous. An order arises from this millions, today probably millions of programmers writing new programming languages and trying new stuff. And some of them come out sometimes with good ideas, with nice concepts, and those will be the languages of, probably the languages of the future.
I'm gonna play devil's advocate here, and I'm gonna restrict myself to the programming languages discussion. Otherwise, we go like into the midnight here. I'm gonna argue that no, that the Lisp school of thought, the Lambda calculus school of thought, like they didn't show up and try to like own the Turing followers or something like that. As far as I know, if you look at the history of programming languages, you have the MIT school, which is where
Yeah.
Lisp originated, and you also have the New Jersey school, and this is
Berkeley,
talked about. Uh,
Richard Gabriel.
Yeah, exactly, that guy.
Yeah, the worse is
There
better.
was a third one. There might have been a third one that I'm forgetting. But the thing was, if you there's a very clear lineage of those two schools originating like computing practice and the languages that originated afterwards. So my point is, I guess, there's much more influence of those like the high priesthood of computing than people like to admit. And if we just inserted like randomly some other school at the beginning, we would have like completely different landscape. So
Uh,
what do you think is what do you think about the high priesthood of like the academics and like the people that originated computing? Or do you think this is really a decentralized process?
I really think so, or at least I like to believe so. And the way I see those institutions, because we have other examples, for example, Bell Labs and some Oxford and England and other schools and not in other areas too. I see them more like incubators for ideas than the originator of new ideas, because they attract people from all the world, from all the backgrounds to there, and ideas come in the people's minds. They don't just arise in a place, right? But of course, these places act as incubators because people go there to work on specific problems. And then they figure out solutions for those specific problems, and those evolve into programming languages, hardware architectures, other engineering solutions. This is how I see the thing.
I wanted to ask this because of course you are an academic, so from my perspective, progress in academia is very incremental, so you're always building upon what the other people are working on. And I'm wondering if maybe we're missing something because I think that people are not really radical enough when thinking about like computing. We're
Oh,
basically stuck at the
especially,
same paradigm for like 40 years or something.
or
So like
even
does
more.
this incremental aspect of research impair the ability of developing like new programming practices and theory as well?
Oh yeah, this is something that I don't know how to answer. I just I'm just sure that the most conservative people I know are all professors.
Interesting.
Conservative in this sense of incremental, trying to find incremental solutions for stuff and building upon instead of throwing everything out and thinking from scratch. This is what I'm. This is conservative in this specific sense I'm saying right here.
I would say so
And
though. I would disagree
yeah,
with you and say yes.
and
This makes progress slower. We have we have freaking Conor Elliott making a presentation saying that people understood it wrong. Like this is the
I don't
proof.
know
A lot
about
of libraries are made upon something. Oh, this is already done. I'm gonna do it a little bit more, a little bit more, a little bit
but
more.
it
And then the
but I don't
original
but I
guy
don't
said all of this is wrong.
uh, I think
yeah,
the
but I
problem
don't
is
see
seeing
this is a problem.
progress. Yeah,
Yeah, but I don't see this is a problem. If I can uh, say just a little bit more about it, I don't see this phenomena as a problem. Because this is touches how we see the role of academia, right? What academia should be doing, and I believe innovation should come from the industry, because industry is the point of contact with the cutting edge problems. This is where the problems, the most important and the most recent problems are. And academia is supposed to, at least this is my view, okay? Academia is supposed to look at this and uh, think about how can I say think about it. It's not thinking the word that I'm trying to, and introspect this and internalize what already happened in the industry world, in the market, in the real world, people trying to solve problems, and after the fact, trying to turn this into a universal knowledge. This is what I see. So I don't see this as a problem of academia. This happening, but of course, people throw a lot of money in academia in all over the world, and of course, they want something, some service, right? Some service back, and our service is knowledge. Where is the knowledge that we are giving back society? Of course, people will ask which knowledge is. And of course, people expect we to be innovative, revolutionary, whatever you want to call it. But this is not what happens. As you just said, we are incremental problem solvers, right? It's one step at a time, and until the thing uh, loses momentum, loses the drive, and we move into another research topic.
I think that I communicated it wrong. I'm not saying that the problem is that there is a problem on people understanding things wrong and building upon that, and then having someone going and saying, no, what you did is wrong. That's not a problem at all. What is a problem is when you pick something that it was already done, and you, instead of you reason about it to see if that even makes sense, you just put more features on it. You make more abstractions on
Ah,
top of
yeah.
that just because it already exists and it's already status quo or something like that. Then you say, oh, this is already state of the art. I, Instead of asking myself if I understood what this means, I would just make more. And that's
I
the
get
This
it.
is a
potential issue,
problem.
at least
Oh
from my
yeah,
point of
that's
view. And something that I want to add before we continue on what Breno said. Breno, when I said about the Lisp functional programmer side versus the Turing people, they are not doing things with the purpose of going against each other. You can do something, whatever were doing, for any other reason, but that doesn't mean that you are not doing something else with another motivation. This is what Adam Smith called the invisible hand, by the way. You are doing something with one motivation, but you're actually doing side effects that represent something else. And you can make a Lisp language just because of the fun of it, but if you're doing that again and you're seeing everybody else doing different, you are doing something else, even if you don't want to. So that was kind of I should have explained that before, but that was what I meant when I said, "Oh, they are doing this against the Turing guys." No, they're not doing that on purpose. Of course not. Anyway, so if you guys do you guys have any more questions? I apologize for the time. It's already um, 8:30, so if you guys have to leave, feel free. So, any more questions or comments? Okay, so I will close the recording now.